All right. Today is the second consecutive lecture about graphs. Today we're going to be doing a problem called shortest path in a graph. It's a pretty intuitive problem. So here's maybe a simple case of an unweighted graph. We'll do weighted later. Okay, but here's a directed graph. I've labeled one vertex S. I've labeled another vertex T. And my goal is to get from S to T using as few edges as possible. All right, so I'll let you guys stare at it, and then I'll ask you guys what's best. This comes up every year. I always forget this arrow. Okay. All right. Can anyone do like 8 or fewer edges? All right. How about 7 or less? 6? Anyone do 6? All right. Seems okay. How do I do 7? So I'll just ask like if I should go up or down and all that stuff. Okay. So starting at S, should I go like up or down? Okay. Go here. Up or down? Down. Okay, I heard both. We'll just try this one out. Down, okay. I guess I have two choices actually. I can kind of go up or sideways. Sideways, okay. All right, and here I can go up and look backwards a little bit or down. Down, right. Okay, and then there's one way that goes up and one that goes down, right. Up. Okay. I can go up or I can go down, right. Up, right, or down, right. Down, right. I can go right or up, right. Right, okay. How many edges was this? 1, 2, 3, 4, 5, 6, 7. All right, I'm not sure if you can do better. It's a good question. How do you certify whether you can do better? Okay, anyway, so that's the problem. Okay, I give you a graph. You want to get from S to T. Maybe it's not doesn't seem so hard with just 18 nodes or whatever, but of course we want to automate this for a really large graph. Yeah, question. Oh, no question. Okay. All right. So in general, let me just set up some definitions. So we will eventually look at weighted graphs. We'll do unweighted first. But the more general problem you're given a directed graph G and the edges are annotated with edge lengths, which can be positive or negative or 0 or something. So I'm using L for L of E to denote the length of an edge. And for a walk, which is just some sequence of edges in the graph, I'm using this notation like L bar of W is summing over the edges in the walk, the length of W. If an edge repeats in the walk, it'll get summed up with repetition. Okay. All right, nothing special. And what we want to compute, kind of just mathematically speaking, formally speaking, is for a pair S and T, the distance from S to T. Okay, so kind of formally, some of these nuances won't come up today because we're only focused on positive edge weights, but it'll come up next time. So out of all walks from S to T, what technically called the least upper bound, the infimum of all the edge lengths. Okay, so what does that mean? So the infimum just handles some of the exceptions. If there is no way to get from S to T, if it's the infimum of an empty set, the least upper bound is just, that would just be positive infinity. Okay, and maybe it's possible to have like arbitrarily negative walks from S to T. Like maybe negative 100 is possible, negative 200 is possible. It can be arbitrarily negative. So there's no oh, it should be greatest lower bound, not least upper bound. Anyway, the infimum would be negative infinity. Okay, so it's really the minimum length walk from S to T, with just the two exceptions being if there's no walk, that's positive infinity, and if it could be made arbitrarily negative, then the answer is negative infinity. Okay, so least upper bound written here is a lie. That should have been greatest lower bound. I'll fix that later. Okay, so that's the kind of formal definition. And one nice thing about this that's easy to check is that the distances will obey the triangle inequality, which makes sense. If I want to go from S to T, going from S to U, and then from U to T will give me a way to get from S to T. So that's an upper bound on the distance from S to T. Okay. So our goal at some level is just to try to compute these values dst, which are otherwise kind of mathematically cleanly defined. Okay, this is just a mathematical definition. It says nothing algorithmic. All right, so how? Okay, so I want to, in fact, this question sort of came up earlier when we sort of found some path of length 7, right? And we kind of stared at it and thought, okay, we couldn't find anything better. And insofar as we all stared at the same thing and we got stumped, that was like our semi-certificate of correctness. We don't really have much evidence that we actually got a correct solution. So whatever algorithm we make is going to maybe need to be a little bit more systematic so that we can really feel good that we find a short path. So I'm suggesting that at some level, just staring at this right away and kind of guessing at the distance of t is a little bit hard because we're skipping, a lot of steps, right? So maybe what we're going to do is we're going to start with, suppose my goal is to sort of figure out dst for all t, okay, including that fixed t. Okay. So we could start with like really easy values. Okay. So I want to try to figure out the distance from S to T for all values of T. So in this example, what is the easiest, most obvious one? Even easier than the neighbors. Oh, itself. Okay. So I feel pretty good that this is the only vertex at distance 0. All right, and then what's next easiest? All right, the neighbors. These vertices are at distance 1. All right, now what would be the next easiest? Just one person needs to say something a little louder. That's all. Their neighbors, right? So I guess that would be, hopefully I do this right. Okay, so these are all the vertices at distance 2. And then, okay, their neighbors. So let me get this right. So I think this top one is not a neighbor. That's okay. That's okay. Okay, so this is everyone at 3. All right, and then I guess we'll just keep finding the neighbors of sort of that previous thing, right? And I keep kind of building out these layers. So 4 kind of is awkward. 4 will start like over here, loop around. So that's 4. That's 4. There's like a chance I'm going to screw this up. That's not 4. That's 4. That's not. Okay, I think that's the 4 layer. Then we'll have, then we figure out all the vertices that are 5 hops away. Again, I hope I do this correctly. You can tell me if I mess it up. That seems to be in the 5th layer. That seems to be in the 5th layer. Oops. As anyone knows, that also is in the 5th layer. And that's in the 5th layer. Damn. If I take too long, then it gets impatient. Okay, I think that's layer 5. Layer 6. Well, I missed one? Okay, which one did I miss? Where would it be? Right bottom. This one? Okay. Okay, got it. Let me try to do that again. Okay, that's layer 5. Yeah. Oh, well, this one is 3, and that makes it, that's what I had in mind. Oh. Oh, I see what you're saying. Okay. It's harder than me. In principle, this is supposed to demonstrate how easy it is. Uh, does that include the bottom one? No, okay. Oh, sorry. Bad habit. All right, is that okay? All right. That means the one uh that we got rid of is a 5. No, keep that. All right, so now the 5 looks like, oh, I don't remember what we were doing. Okay, I'm just going to circle these. That's a 5. Um, this one here is not a 5. This one is a 5. Um, oh, that's a 4. Okay. All right, so the 4s are 4, 4, 4. Okay. No. Okay. 4s. Okay. 5s are that one that's already circled. This one is a 5. This one is a 5. This one is a 5. Right? Okay. All right. That's the 5 layer. Now we're on to 6. This is a 6. That's a 6. That's a 6. Is the last one a 6? It's not, right? All right, so I think this is the 6th layer. Which one? Uh, There's a middle one. Right. Okay, that I already circled. Right. Fun fact, when you're in front of a lot of people, you're like proportionately dumber. All right. 7. That seems to be a 7. That seems to be a 7. We must have done. Oh, okay. All right. Those are 7s. Okay. And then finally, this would be 8. All right. Hopefully that's correct. But hopefully at least it makes some kind of point clear. All right. But what's sort of the takeaway? Now we've come to the same conclusion that T is 7 steps away. But we feel good about that insofar as we feel good that we figured out everything that's 6 steps away. We feel good about 6 insofar as we figured out everything that's 5 steps away. Sorry, from your point of view, 5 steps away. 5 insofar as 4, 4 insofar as 3, 3 insofar as 2, right? When we write these annotations and we kind of build this up, we have actually a little bit more of a certificate or a proof that it really is 7 steps away, right? At some level, any algorithm that you're going to prove to be correct kind of needs to show its work in some way. It needs to have some kind of transcript to be able to prove it's correct. Okay, so anyway, this is what I did ahead of time. There's only like a 1 in 5 chance it's correct. Okay, so we're just going to take this idea and turn it into an algorithm. Okay, we'll do it exactly as we did before. So I'll just set distance of, so okay, I'm going to make these distance labels for all these vertices. This kind of distance of S is just some table I'm filling out. Okay, And then at the end, I'll just return all these distance values, and that's, yeah. So I want distance of S to be equal to ds of S, but otherwise they're different things. Distance is something from the algorithm, and D is the true thing. So we start with S. We know that S has distance 0, so I set distance of S to be 0. Okay, and then otherwise I just loop through. I build out layer 1 by looking at layer 0 and getting all the neighbors. And I build out layer 2 by looking at layer 1 and labeling all the neighbors that haven't been labeled already, because some may have already been labeled distance 0, in which case I wouldn't label them again. And we just build them out one by one. Okay, so very simple. And, very simple thing from first principles. And it's not hard to make this linear time, because if you think about it, right, like you start at the source, and then to build out the next layer, you just look at all the edges leaving the source. So you look at the edges leaving the source once to build out layer 1, right? And that'll gather a list of vertices for layer 1. Then as you go through the vertices in layer 1, you look at each vertex each edge leaving layer 1 once. As you build out layer 2, and you don't repeat if it's already been labeled. So as you build out, you're only looking at each edge once. Okay, and you're only labeling each vertex once. So running time will come up to n plus n. Okay. So kind of very simple, and it works. Okay. All right, so I think the algorithm is kind of very intuitively clear. I think you all believe that it works. I'm not really trying to argue that it works. I'm more interested in sort of how do I articulate that it works formally. Okay, so just trying to take our intuition and kind of get it down on paper and communicate it. Okay, so how might I try to prove the algorithm is correct? So I want to argue that for all vertices V, it labels like distance of V is equal to ds of V, which is the true distance from S to V. How might I try to structure an argument, formulate an argument? Yeah, maybe a contradiction. Well, suppose I already had slides prepared to try to do a proof by induction. Okay. Well, yeah. How might we frame the inductive argument? Yeah. 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 Okay. So I think that's the idea behind the proof. But just before that, usually we kind of state some statement where k is involved, and then we'll then prove the statement. So what would be like an example of a statement we prove, if that makes sense? Sorry. Well, the first node may, for example, be a base case eventually. Smaller graphs. Oh, by removing an edge or something. Okay. Okay. So at some level, by induction, you usually want to find some parameter or something getting smaller. So the idea is can you somehow do an induction where you're making the graph smaller? Like you do something and you make the graph smaller. Um, can you? Uh, I'm not sure, but maybe. Okay, maybe. Okay, that's maybe an okay. Just play with it because it's fun idea. So actually, yeah, maybe it is possible. Um, if you wanted to, Do induction on the size of the graph. Any ideas? Yeah. Oh, okay. So, okay, in the reachable homework problem, we had something like uh, maybe there was S. So it was something like reachable from S to T or something, right? And the idea was, oh, you try looking at different vertices here, V1, V2, V3 or something, and before recursing on V1, maybe we would delete S and all the edges incident to S or something like that. So I feel like that's also, that will give an inductive argument in the sense that vertices are going down, but it also feels like it's analyzing a different algorithm than the one we're analyzing, in the sense that breadth first search doesn't feel like it's deleting S or edges from S or something like that. We probably could have written a different algorithm that maybe does that, but it might not have been as fast. All right, so just for fun, if we wanted to play with that idea, possibly one way to try to do this is like to do something like let v1, v2, vn be sort of be the order in which vertices are labeled. Okay, if you did want to do this argument, so I'm only going to sketch it and probably should be fleshed out a little bit more. So v1 would always be s, and v2 is whatever gets labeled second, v3 is whatever gets labeled third, right? That's some ordering. And then you can try to argue that if I had run v, yeah, let me say vn minus 1, vn. If I had run this algorithm, breadth first search, on the first n minus 1 vertices, and if I remove the nth vertex from the graph and all of its incoming edges, I can try to argue that breadth first search on those first n minus 1 vertices is doing the exact same thing as our algorithm would do for the first n minus 1 steps. And then by induction, try to argue that it gets the n minus 1 steps correct, and then deal with the nth vertex. Is that compelling? I don't know. I kind of made this up on the fly. But that might be a way to do induction on the number of vertices by trying to, in other words, remove the last vertex that gets labeled. By induction, argue that breadth first search is going to be correct on the first n minus 1, and then try to make some kind of argument that your algorithm running on all n vertices is going to coincide with the vertex, with the same algorithm run on just the n minus 1 vertices. That'll then say the n minus 1 labels are correct, and you can add the n. So that one step where you say the algorithm is coinciding might take a little bit of while to articulately write down, but okay, that might be. Okay, whatever. Let me, so that's the one way, but let me keep this rolling and at least maybe do a different approach. Okay. So this is close to the original idea of just focusing on the vertices of a particular distance k when we do the argument. Okay. Suppose, at some level, there's kind of two kinds of vertices. There's the vertices that are truly at distance k from S. And then there are the vertices that we label and claim is at distance k from S. So that's two different sets. I want to argue they're the exact same. And I want to argue they're the exact same for all values of k. Okay, so this is just setting up the proof. This is the claim we can prove. And, nice thing about it is there's like a natural k in there that, we can do induction on. Right? So what might be the base case then? Base case might be 0. And that's pretty easy because clearly S is the only vertex truly at distance 0, and S is the only vertex being labeled 0. Okay, so that's not too interesting. So in the general case, we have some distance k greater than 0. Okay, so, if I write down just a definition of BK, so that didn't go as I had hoped, but that's okay. All right, so ignore the yellow. But, so BK is the set of vertices that the algorithm labels distance K, right? So if we think of what the algorithm does, is it looks at everything that was labeled distance K minus 1, that's not already labeled, and looks at their neighbors, and if it's not already labeled, gives it distance K. All right, so that's why I tried to describe in BK and somewhat compactly. So it's all vertices that are not in B0 through BK minus 1, so it hasn't been labeled yet. But there's some edge going to V from some vertex U that's in BK minus 1. That's what the algorithm is doing. Okay. And then now where does induction come in? So by induction, when I look at each of those BIs where I is less than K, what do I know about it? Okay, it's equal to AI. Okay. So in other words, so it's equal to this set, which we can describe as all the vertices that are not truly at distance less than K, but it has an edge coming in from some vertex that's truly at distance K minus 1. Okay, so that gives it distance K. So what we're really describing is the set AK, like we wanted. Okay, so, and this is more or less exactly what we said when we kind of thought up the algorithm. Insofar as I got layer 2 correct, I know I feel good about getting layer 3 correct. If I get layer 3 correct, I feel good about getting layer 4 correct and stuff like that. Okay. And the part where I say, insofar as I got layer 3 correct, is that induction step, or is where we apply the induction hypothesis. Okay, so anyway, just formalizing some intuition. All right. You guys have probably heard of this algorithm before, breadth first search. Usually it's just presented in terms of a queue. Okay, so an alternative way to implement the exact same algorithm. So the way I present it, you're deliberately building out these layers. It's a little easier to prove that way. But what you could do is you could just like have a queue. So a queue is like a line. Something comes in the back and it comes out the front. And every time you label a vertex, you just put it into the queue. And then you take out a vertex and you look at its neighbors and you label it. Okay. And what's going to happen is that layer 1 is going to move through the queue, and then layer 2 is going to move through the queue, and then layer 3 is going to move through the queue, so you'll get the same algorithm. Okay. All right, same algorithm, 2 different implementations. All right, so much for unweighted graphs. Let's generalize this a little bit to positively weighted graphs. Okay, so now the edges have some positive weight. You want to go from S to T and minimize the sum of those edge weights. Okay. All right, so I guess I gave you guys another example. I'll let you stare at it a little bit and then ask you what the solution is. All right, what's the best distance anyone got? $15? Okay, how do I get 15? Do I go up up to the right or down to the right? Huh? Oh, okay, up to the right or down to the right? Okay, seems like up to the right is more popular. I'll go with that. Up to the right or down to the right? That one seems obvious. Okay. Uh, Up to the right or down to the right? Or yeah, just right, I guess. All right, so that gives 15. Did anyone beat 15? It's 15. Beautiful. I mean, I always find this just interesting because you stare at it and it's like, it's probably 15, but it's like, is it really? You know, you have to, at least in my mind, I have to like race through all the other possibilities to feel good about the solution. Okay, so it had been even mildly more complicated, it would take that much longer. Okay, fine. So you all get a grip of the problem. Now we just talked about unweighted graphs. So just as like a thought experiment, let's suppose that the edge weights are integer, like it's drawn here. But in general, the edge weights could be weird fractional numbers and all this stuff. But imagine they are all integers, like in this example. How could I, at some level, don't worry too much about running time, kind of reduce from integer weighted setting to an unweighted setting? How can I make this problem look like the unweighted setting we just solved? So, okay, so you want to add vertices maybe. Like I want to take an edge, right? If I take this edge of weight 4 and I add 3 vertices in the middle, and I think of those little segments as edges of weight 1, right? I'm just splitting them up. Taking the long edge of weight 4, turning it into 4 small edges of weight 1, right? So something you can do is discretize, so to speak, the edge weights and turn it into an unweighted. So you get something like this, right? Okay, so, and then we could just run the algorithm we just did, right? So what's the algorithm going to do? Well, it's going to build out layer 1 and layer 2, and this is going to be challenging, 3, 4, 5, 6, this kind of thing, right? So I can run breadth first search on this unweighted graph, and it's going to build out all of these layers, and for integer weights, it's going to be correct, right? We've already proven that it's correct. Okay, there is a drawback to this approach. What is the drawback to this otherwise kind of conceptually clean reduction? Runtime. So what happens to the runtime? Right, so, well, I guess I did all of them. So, I mean, here those edge lengths were pretty modest, like the biggest one was 7 or something. But, uh, you only need log n bits to describe a number as large as n, right? So there could have been edge weight of weight billion, gajillion, gajillion, and it only needed like 20 bits to write down or something, right? So suddenly our m plus n running time, n would suddenly become billion, gajillion, gajillion because there's some huge, humongous edge weight out there. The input size is still looking like log of billion, gajillion, gajillion because that's how many bits it takes to write down a big number. So you're looking at an exponential time algorithm, technically. Okay, so the only issue is running time. Okay, so how could we sort of keep the same ideas? Because I like the fact that this is correct, right? I like the fact that when I draw the layers, I know that T is, in that picture, 16 steps away. It clearly did something wrong. But, uh, building out the layers so I can also certify, the solution. So at some level, how can I maybe implicitly do this, but make it a little faster? Yeah, so at some level, like, this is kind of boring, right? Like, do I really need to figure out layers 1 and 2 to realize that layer 3 is, that next closest actual vertex? Do I really need to do, I guess 5 has, but do I really need layer 7 or 8, which has no red vertices in it? If I can just kind of figure out what the breadth first search algorithm would do, kind of figure out the next closest real vertex and add it and sort of skip all of those sort of unnecessary layers. Then I don't necessarily have to pay this cost proportional to the edge distances because I can skip, all those silly intermediate vertices. So that's what we're going to do. Right? We can skip the empty layers and just figure out what's the next layer I need to build out. So from S, I would just say, oh, the shortest edge is 3, so that's going to be the next layer. And after that, I would be trying to figure out, oh, what's kind of the next closest one. So I would look at edges leaving S, as well as edges leaving that vertex at layer 1. And I would conclude, oh, there's a vertex that's distance 4 away. Okay. Same thing implicitly as before, but skipping some work to make it faster. Okay, so this is the algorithm that was proposed by Dijkstra, okay, in like the 50s. And so it's very, very similar to before. I mean, the first step is the same. I'm going to set distance of S to be 0 because that's the easiest one, right? And now I just need to write some code to figure out, hey, what's the next layer? What's the next vertex I should be trying to label? So, I mean, there's probably different ways to do it. I just try to write it this way because I thought it was clean. So at some level, I'm looking at all the vertices. I'm looking for vertices V, where V has some edge coming into it from some vertex U, where U already has some label. So I've already computed distance U. So it's in a previous layer, so to speak, right? And I'm looking at the distance U plus, the length of this edge, if this edge was E. Okay, and that sort of estimates some distance to V. So out of the unlabeled vertices V that has some incoming neighbor that's already labeled, I want to minimize the distance of U plus the length of that extra edge to get to V. Okay, that's what the 3 points are meant to describe. And whatever vertex V minimizes the sum, that becomes my next label. Okay, but it's just, implicitly shortcutting or leaping over all of those intermediate integer layers. Okay. We'll worry a little bit more about how to make this really, really fast a little later after thinking about the correctness. Okay. All right. The algorithm clear? I mean, I know there's new notation, so it takes a moment. Okay. All right, let's try to prove this thing is correct. I mean, at some level, we probably feel good about it because we've drawn all these pictures, and there's at least some clear idea that I think we're kind of all in agreement on at this point. So I just want to kind of formalize this and get this down. I don't always trust my intuition. So, like before, if I want to prove something's correct, I first need to come up with some kind of sentence that structures a proof by induction, okay, just to get the thing going. I mean, at the end of the day, I want to prove the algorithm's correct, but that doesn't really get me ready for a proof by induction. There's no kind of natural Ks or anything like that. All right, so what might be a way to frame a proof by induction? One thing to keep in mind is that although in the pictures before, when we developed ideas, I was thinking about integer weights, I now want to prove this for any positive weights. Right, so it's not an easy question. It's really a probing question because at some level, can you find some structure, some numbering or ordering or something being enumerated that you can kind of count down or something on, right? So in other words, can you find the hidden structure of the algorithm is sort of what this sentence represents. So I'll say one thing that's kind of weird. Last time we were able to use the distance labels themselves to do a proof by induction. I did, oh, distances of label 1, distances label 2, distances label 3, because by coincidence they were integers. So we can do induction on integers. As real values, it's not so clear, right? So that is sort of an issue. It's hard to find the thing. It took me actually a little while to think about it when I was writing the notes. The minimum. The minimum distances of set of neighbors. Uh, well, at some level, that's not quite a coherent sentence to prove. But whether there's ideas in that, I mean, I think it's circling around the right ideas, right? We are going to end up doing something kind of where we grow out the neighbors and stuff like that. That's true, but we need a statement before a proof at some level. Yeah, yeah. Okay, that's not wrong. So technically, we won't do it this way because it's a little messy but uh, if you kind of like look at all the arithmetic you can do out of the edge lengths, right? You can add and subtract and stuff like that. There's sort of like a minimum non-zero value you can generate. It can't be like arbitrarily small because there's only finitely many combinations. So that gives you kind of like a discrete unit. Uh, and then you can kind of do, in other words, you can try to do like units of a common denominator, a sufficiently small number so that all differences that might arise are a multiple of this small number. And then try to do induction on this. Um, that would kind of be okay, but it would be a bit messy to set up the part I just described. Um, Let me give a different idea, which is interesting. I think it's interesting because okay, actually it came up earlier, so it's less interesting now. But suppose I numbered the vertices v1, v2, v3, v4 in the order in which they're labeled by the algorithm. Okay, and now I'm going to try to prove each one is successively correct by induction. Okay, I mean it's clear in hindsight. It makes sense in hindsight, and at some level, it's very similar to how we think about the algorithm, right? Because we get S correct first before moving on to the second vertex, third vertex, fourth vertex. What I think is kind of interesting about this style of this framing is that V1, V2, V3 did not come from the problem statement in some sense, right? It's sort of based on what the algorithm did. It's sort of dynamically generated by the algorithm. It doesn't, if you only had the problem statement, your input is a graph with edge weights, you wouldn't have enough information to formulate this statement. But since we're proving the algorithm on the data, we can actually use the ordering produced by the algorithm to set up a proof by induction. So that's just something to think about. Okay, so I'm going to number the vertices in order at which they're labeled. And for each I equals 1, 2, blah, 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 I'm going to argue that that vertex is sort of everything is correct. So in particular, for I is equal to 10 or something, I want to say that V10 is the 10th closest vertex to S, or from S, and that the distance label is the true distance from S. Okay. And then we just have to go through I equals 1, 2, 3, stuff like that. All right, so what would be the base case? S, which is I equals 1, right here. Yeah, the base case is I equal 1. The vertex labels S first. It gives it distance 0. We already know that's correct. Okay. All right. So we know that's correct. No big deal. So in the general case, I is bigger than 1. Okay. So VI is whatever the algorithm labels for the ith time. Not necessarily at the moment, truly, the ith closest. vertex. We want to show is the ith closest vertex, right? So if I wanted to maybe describe what VI is a little more declaratively, I guess it's sort of similar, but at some level it's, all right, so out of all edges, E going from some vertex that's already labeled, from some Vj where j is less than I to some other x, it's the endpoint, the head, so to speak, that's minimizing the distance to that first point plus the edge, like we did. So that's one way to describe somewhat compactly what the algorithm is doing. Okay. Head is the where the edge ends. I forgot to say that in some previous lecture. Tail is sometimes where it starts. Head is where it ends. And then when I write like Vj comma x in parentheses as opposed to in a set, the first one indicates where it starts, and x, the second one, indicates where it ends. So if it was a comma b, it's going from a to b. Usually if it's an undirected edge, I use a set notation. At least I try to remember to, since it doesn't really matter the order of the vertices. Okay, so that's one way to describe this vertex of the algorithm labels for the ith time. As far as the true ith closest vertex, oh, one sec, I forgot to mention something. Right, okay. So, and then for what it's worth, that quantity, distance Vj plus Le, is what becomes the label for Vi. That I forgot to mention. Okay, now what about the actual true ith closest vertex, right? The true ith closest vertex can be described similarly, except it's based on true distances and not on labels, right? So the 10th closest vertex should be the one that, based on the previous 9 closer vertices to S, has the minimum kind of going to that vertex plus taking one more edge. Okay, so it's really the same thing, except it's replacing the distance label with the true distance. So it should look similar, except I've replaced distance with the true ds Vj. Okay, and of course, this combined quantity represents that true distance to x, or the true distance to the ith closest vertex. Okay, so those are just like two facts. And then how do we finish the proof from here? I want to argue that these two things are equal.
Distance of Vj is equals to ds.
Because? So you just need to replace one word with another, right? I want to argue they're equal. Why are they equal? Not because of the minimum. I mean, if you just compare the two sentences, right? We only have, the edit distance is very small. That and that is the only difference between these two sentences. So if I can argue those things are equal, then we're done. Right? Yeah. Yeah. So the key word is just induction, right? So by induction, because j is less than I, those two are the same. Okay, and that just closes the argument. And I think this argument is also intuitively very similar to how we thought about the algorithm. I figured out the 9th label and I knew it was correct, and that's how I moved on to the 10th. All right. Okay. All right, so I just kind of formalized something that I think is otherwise not too surprising. All right. Great. Okay, so let's look at the running time of this algorithm, at least kind of naively. We'll worry about speeding it up in a moment. Okay, so I was looking at like this code here. You know, how long would this code take? So assume in this step A, you just like actually do an old-fashioned loop? How long might this take? Sorry? M plus n squared. Okay, so maybe let me break it down. So let me say how many, okay, so we have some loops. Okay, so how many iterations might I do of step 2? Okay, we'll have n iterations. And how long will this loop take? M plus n? Is that what we said? Okay. Yeah, for some reason, computer science has chosen to focus on the 2 letters that sound and look the most similar, M and N, and also I and J. And that's like the hardest part of this class. Okay, so this will take M plus n time, but you really just have to loop through the edges, look at the first start point and see if it's already labeled, and then look at the other point. Okay. All right. And then I do some minimum of the things I compare, so that's not so hard. So roughly the running time should multiply these things together. And so we'll get some like n plus n time. Okay, m is probably bigger than n. At least if you run like depth first search first and get rid of things that aren't reachable, but it's really like mn. Okay. So the question then is, can we do better? Right? Can we make this thing a little bit faster? I'm guessing maybe many of you have seen this before. So this is the first time in this class so far that we're going to try to make something faster using data structures to try to facilitate some of the steps. Okay, so at some level, the bottleneck, right, this loop is like kind of killer. And at some level, like, if I'm just doing a naive loop, I'm sort of recomputing like a lot of stuff, right? Even though like, say between iteration 9 and iteration 10, number of choices of u has only gone up by 1, right? That distance u. I've only added like a 10th vertex or something. So probably the first 9 vertices, I shouldn't have to recompute the corresponding values. And I should just, compute the ones for the new vertex that was added and compare that to some of these existing values, right? So to set that up, let's like define some notion of like tentative distance. Okay, so we have all these unlabeled vertices. We haven't really figured out their distance yet, but like we sort of have these like candidate values where we use a previous distance value and we add an edge, right? And we don't really know if that's the best one yet, but we have some kind of tentative values so far. So I'm calling that the tentative distance to a particular vertex. So for an unlabeled vertex V, it's just the minimum of this kind of quantity we're fixated on over all choice of u that's been labeled so far, and plus the length of the edge from u to v. Okay, so we haven't finalized it, but so at any point in time, every vertex has some tentative distance. It might be positive infinity if there's no choice. Okay, and the idea is that each iteration, I label one more vertex u, and that will update that might update some vertices tentative distance, but it's not going to update all of them, right? I should just look at u and the edge is leaving u, and only for those v's check to see if I have something better now. Okay? So we're going to incorporate that. And to kind of manage who has the minimum, who has the best tentative distance at any time, we'll use a heap, a min heap. Okay, so I'm kind of assuming that most of you have taken like some kind of basic data structures class before, but what is a heap? So it's a data structure, okay? So some kind of blob, you put things in, you take things out, you ask it questions, okay? The 3 operations, okay? So for us, a heap is going to be managing these like key value pairs. The values are called priorities sometimes in this context, okay? And so you have three operations. One, you can insert a key with a particular priority. And it just goes in the heap. It goes in the queue. Second operation is you can remove the key value pair with the minimum value or the minimum priority. Okay, so you can minimize, you can kind of keep extracting the min. Okay. And then the other is you can decrease the priority of an existing key value pair. Okay, so you might have already inserted some key with priority 10. Later you want to decrease it to priority 5. There's some operation to do that for you, and it'll be reflected in the next remove min. Okay, so you're just kind of sorting some things under the hood for you. So the simplest implementation that we, basically teach will take like log n time for each of these operations. Okay, this also gives you a different sorting algorithm because you can just insert all n elements and then remove them. Okay, so let's think about how to first use that. Okay, so, all right. So here I've redone this so-called Dijkstra's algorithm, the shortest path algorithm, based on this kind of notion of tentative distance. So I've labeled, initially I already know that I can go from S to S with total distance 0. So the tentative distance to S is 0. And for everything else, I haven't really explored anything yet. Nothing is labeled. So everyone gets tentative distance infinity. Okay. So, and then we'll make a heap over all the vertices using their tentative distances as that priority. And now I'm just going to loop through and keep removing the vertex with the minimum priority, the minimum tentative distance. The first time it'll be S because that got labeled 0 or tentative distance 0 and everything had positive infinity. Okay. When I extract S, now I have some edges leaving S, and I use that to update or potentially update other vertices tentative values. So when I extract a vertex V, that's the next vertex that gets labeled, and its distance becomes whatever was sort of that best distance we found so far, that tentative distance. Okay, so I label it. And now I go through and I update everything. So I look at all the edges leaving V, right? It's going to some other edge W, and I compare whatever I thought was previously the best way to get to W with my newfound way to get to W. So if that value goes down, if I do make some improvement, I'll update the heap, let the heap know that value went down. Okay, so the next minimum, remove minimum, it'll be reflected. Okay, so this is kind of streamlining the same high-level logic as the earlier algorithm. Okay, using a heap to sort of help us find the next closest vertex quickly. All right? All right, now how long is this going to take? Say all these heap operations take log n time. Okay. All right. Okay, so initially, you insert all of the things into the heap. There's n vertices that take like n log n time. No big deal. How many iterations of this loop, step 3, might we have? N, right? Because each vertex will only get pulled out once. Once it's out of the heap, it's out of the heap. Okay, so that, I thought I had something written. Okay. Oh. Okay, whatever. This is n iterations. And then the first step, to remove a vertex will take log n time. Right? So that's kind of n log n right there. I set the distance, and now I look at each outgoing edge, and I potentially update that priority, right? So again, an update also takes log n time. Okay. Now, how many times total will I execute this step 3.c? How many times will I loop over edges and stuff like that? Right? So if I can just figure out how many iterations total of C we have, maybe over the entire course of the algorithm, M. Because each edge we only look at once. So I only look at an edge from V to W right after V got labeled. So I label V, I've set the distance, and then I look at its outgoing edges. I never look at those edges again. Okay? So added up over all the outer iterations, I'm only looking at each edge once. All right, so it's only once per edge overall. If I put that all together, what's my running time? M plus N log N. Yeah, I think I just wrote M log N because I'm assuming M is bigger than. Okay. All right. Okay, so that's pretty good, right? We went from Mn-ish running time down to M log N by incorporating a heap. All right, so it turns out you can do even better than this, all right, with the use of a spectacular data structure. So this will take far too long to prove, but we might do it by the end of class, depending on how the schedule plays out. All right, so we have the same, this is called a Fibonacci heap. We have the same interface, so it's still some kind of min heap or priority queue. Okay. Now, it has the following guarantee. So last time we said, oh, every operation takes log n time no matter what. You don't have a no matter what kind of guarantee with the Fibonacci heap. So you have something that's a little bit different. It's called amortized analysis, which will be a topic towards the end of class. So right now I'll just state what it is, okay, and figure out how to use it. So if you make I insertions, D calls to decrease key, and R calls to remove min, okay, maybe 100, 200, 300, okay, then the running time will always come out, the total time spent by the algorithm will come out to I plus D plus R log n. Okay? It doesn't mean that each insertion took constant time. It doesn't mean that each deletion took constant time. It doesn't mean each remove min took log n time. But in the aggregate, sort of like on average, each I on average in hindsight took constant time. Each deletion on average in hindsight took constant time. Each remove min on average took constant time. So this kind of like on average type of analysis where you look back in hindsight, that's sort of called amortized analysis. It's a little bit more flexible, right? Because you could potentially do a lot of work here and then do less work later on or something, right? You don't have to always uniformly spread out your work. It doesn't have to be like doing log n time every operation is more restrictive, right? Now I can kind of do some batch processing and stuff like that. So that's called amortized analysis. It's very useful, and we'll come back to it later in the class. But anyway, this is a kind of probably our main example early on in the class of an amortized data structure. All right. So let's just figure out how to use this thing and what happens. Okay. So if I use Fibonacci heaps instead of regular bin heaps, okay, and I have this sort of on average or in the aggregate guarantee. Okay. So now what? So I have, how many iterations do I have of 3 again? N, right? 1 per vertex. Oh, I made the same mistake. All right. Now when I remove a vertex, the minimum tentative vertex, okay, this says that it's going to take like log n time on average, right? If I did 100 remove mins, it's going to add 100 log n to my running time. And then I set the distance, and then the only other time I use the queue is down here when I decrease key, okay? And this one takes constant time. This should have been on average. Okay, so n outer iterations. Okay, and again, I look at each edge once. Okay. So all that put together, now what's the running time? Hmm? Okay, so n log n is coming from here. Okay, so n log n is one part, but it's not the entire running time. M, so we are still doing, for every edge, constant work on average. So you put that all together, and you get m plus n log n running time. Okay, so we're able to go from m, we move the log n off of m. And m is usually at least as large as n. It could be as large as n squared, in which case it's great that we move the log n off of it. Okay, so anyway, so that's the use of this spectacular data structure called the Fibonacci heap. Okay. All right, that's all I have for Dijkstra's algorithm. What I wanted to do in the remaining 5 minutes is to sketch out kind of one problem that hopefully will get you going on the homework. Okay, so this is just an exercise. It's a variation of what we've been doing in this class. Okay, so before we're trying to find the length of the shortest path or walk from S to T. Okay, now I'm asking for the length of the shortest walk from S to T that uses an even number of edges. Okay, so just for our example, what is the length of the shortest way to get from S to T using an even number of edges?
Are they also or weight?
So yeah, the weighted length. So you take your walk, you add up the length, and that's your weight. You try to minimize it. But the number of edges you use has to be even.
Not the weight, sum of weight.
The sum of weights can be anything. It can be odd, it can be even, it can be irrational. Sorry? 18? Can you, okay, 17? I heard, so, okay, so how do I do 17? I'm not, okay, do I go down right or upright? Down right? 3, okay. Now do I go upright or right? The 4? Okay. 6, 10, 17? It's probably 17. And even the same question of like, how do I know I got the answer right? This is even more painful, like, right? Okay. All right. So at some level, it doesn't seem like that hard of a question. All I've done is say, yeah, it's be even now. But how do we solve this? Right? How do I solve this question? How can I come up with an algorithm for this? Yeah.
Just do it the way we did previously, but once we get the shortest distance, like in terms of weight, check the number of edges for that. If we don't, then we move on.
Okay, so I can try to compute. Okay, so the idea was this kind of similar algorithm to before, but whenever I kind of am doing some tentative distance thing, check to see if the distance so far is even or something like that. I mean, I've used an even number of edges so far. So you have to be careful because at some level, there's no way to get here with an even number of edges. So your algorithm, like, it would just like never, like you would never be able to get past layer 1 because layer 1 will like always have one edge. So you'll never label, so if instead of labeling distance, I'm labeling even distance or something, right? But I'll never end up setting any of these values to even distance. The algorithm will kind of get stuck, right, at the very beginning, because only one edge leaving S. Yeah. Can you maintain two priority queues, one for odd distances and one for even distances? Okay, so, all right, so some level, can I take this code and make it roughly twice as big, where I'm trying to manage two sets of distances at once? And then afterwards, can I go through and prove the thing is correct. It's going to be a lot of work. That much is at least clear, right? It's going to be twice as complicated or twice as long at least. And I don't even know if there's going to be some subtle interaction between them. Yeah? Yeah? Okay, so here's a trick, right? It's going to be a very useful trick in the class. So we're going to propose an idea. I think this is what's being suggested. We don't really make a new algorithm at all. Okay. In fact, maybe I'll give that as a hint and give you guys one more chance to guess. Don't invent any new algorithm. Try to make a new graph.
Like combining two nodes.
Yeah, try to make a new graph that I can just run our old Dijkstra algorithm on. Because I don't want to reprove anything. Like it took 45 minutes to just do that, right?
How about just dropping the,
Huh?
how about just dropping the,
Dropping?
nodes with, in the programmer, right?
Well, maybe one idea, this is not the ultimate idea, is that for every two edges in a row, I can think of that as one edge, right? Because you're allowed to take an even number. So you can do stuff like, oh, I'll add this edge, it has weight 8. I'll add this edge, it has weight 9. Because that reflects 2 steps, and I'll only keep the 2-step edges. Okay, how many edges will I end up in that graph? Yeah, it could be like n squared, right? It could suddenly become a dense graph. You run Dijkstra on it, you're looking at like an n squared running time. That's not a bad idea though. That will work, and that's obviously correct because Dijkstra is correct, and I know exactly what's going on. Okay, so that's actually a better solution than before. Okay, can we do even better? I want to do something that doesn't blow up the edges so much. Yeah.
Can we find a walk from S to T? All walks which only have even number of edges.
There's too many. There could be exponentially many.
But then we still they remove the part of it.
Okay, exponential divided by 2. Now stick with this idea, trying to change the graph.
So we go twice and we add more by to the
So you go twice?
we can add edge between two nodes and each between the nodes there must be equal
Oh, but that's similar to kind of adding all these edges for all the 2 hops, right? So here, every time I have 2 edges in a row, I create an edge. That's sort of what you're saying? Yeah, so that will generate, so the result is that you might have n squared edges in your end of graph, which is bigger. So I want to do a good idea, but I want to do one where the edges don't blow up so much.
like get the 4-hop edges, but if you like go back to another vertex that like we've already calculated, we just keep them on.
I think you were screwed as soon as you said maybe. Like, no, again, it's not from doing 4 hops and 8 hops or something. That will still generate a lot of 4 hops. You're going to get even more edges. Yeah.
You split every vertex into 2 and even in a not copy, and then for the edges connect even draw them.
Okay, so what we're going to do is we're going to make a new graph. Okay, I'll call it like V prime. And it's going to have like, for every vertex in the original graph, I'll make 2 copies, V odd. I'll call it V odd and V even. Okay, so I'm inventing 2 new vertices for every vertex in the graph. Okay, and I'll make a set of edges. Okay, where for every edge, UV originally in the graph, I'll draw a picture and I'll make it very clear in a moment. I'll make an edge from U odd to U even, V even, and from U even to V odd. Okay, so I've taken every vertex and made kind of 2 vertices, and I've kind of taken each edge and replaced it with an edge that's kind of going across parities. So one way to think about it is like this. So originally you have some graph like this with some edges, right? And now what I've done is I've kind of created 2 copies of the vertex set, okay? And for every edge, that's like going from here to here in the graph, okay? Okay, so one sec. This is sort of like the, I'll call this the even vertices, I'll call that the odd vertices, and I'll call this the even vertices. And for every edge like that, it's going from there to there, I now have an edge going from the even copy to the odd, and the odd copy to the even, okay? And now what? I'm going to look at S even, okay? And like T even, they're both somewhere in the even, okay? And I'm going to have to ask for the length of the shortest path in this graph, and we'll also carry over the edge weights with the same weights. I'll look for the length of the shortest way to get from S even to T even. But what's going on? V even means these are the vertices I can get to with an even number of edges, right? Because I can go up, down, up, down, up, down. So if I go from S even to T even, I know I've taken an even number of edges. If I'm going from S even to T odd, I know I've taken an odd number of edges, right? So what's happening is that I'm adding memory, right? That little extra key or label or annotation, even odd, is remembering that you've taken an even number of steps so far. It's remembering that you've taken an odd number of steps so far, right? I'm actually expanding the number of possible states, right? And encoding it. Okay, so I just have to find a path in this graph. How many edges have we created? Just 2 copies of every edge and 2 copies of every vertex. So it might seem clumsy and not clever, except you haven't increased the size of the graph by any substantial amount. This is actually a very good, slick, economic idea. Okay? The last thing I want to mention is that, okay, so the ideas make sense, the proof makes sense, you probably don't doubt the correctness. But ultimately, to prove it, you need to do an if and only if. So you need to kind of go both directions. And even whatever walk here will correspond to a walk in your auxiliary graph from between the even vertices, and do the mapping and show it preserves the edge weights. And show that a walk between U even and V even here corresponds to an even edge walk in the original graph with the same edge lengths. So you have a one-to-one correspondence. So this way you can say that when I find the shortest even length, shortest walk in the auxiliary graph, that gives me exactly the shortest even length, even edge walk in the original graph. So you need to do a back and forth to establish that your reduction is correct. You don't have to reprove that Dijkstra does the right thing. You just need to understand that interpreting Dijkstra does what you expect based on your auxiliary graph. Okay, so you get a lot of problems like this where the key is not to change the algorithm, but to change the input. You have to understand what the algorithm does, but otherwise you change the input. Okay, I'm a little over, so that's it. Thanks, guys.